And if you remember, last time we covered the transformers. And what the transformers make use of, they make use of efficient magnetic flux transfer through a certain construct or through a certain material. And that enables us to construct a useful electronic device or tools. And when we learn about the magnetic flux, we saw that whenever we have a flux, the rate of change of flux versus time, we have the creation of a battery. I'm just calling it this way. So we have some power supply, which we have generated, and this power supply is as a function of time. It's not a DC, it's an AC. And rather than this, we have also the possibility to construct or to create effective units which can be measured by the following. So if you have any charge, there will be an effective electric field E prime, and this will drive the charges around. So if we have the charges around moving, then we can say that effectively we have some power supplier or we have a battery and so on. And sometimes this key element, this is made possible by lines or wires that cut the magnetic field. So if we have a magnetic field flowing, so let's say that there is magnetic field flowing in this direction of my fingers. Then I move this pen across, okay? Just because this pen is cutting the magnetic field lines, we have the creation of an effective electric field or the creation of an effective power supplier, okay? So we call this magnetic field cutting lines. And if we have, and at the same time, imagine for a moment that you have a circle. So let's assume that we have two wires, they extend like this. And then you have also a wire that extends like this. You can connect a resistor here. And then you can rotate this one clockwise or counterclockwise. So if we rotate this one, because of the magnetic field of Earth, you're going to see a current flowing across these wires, okay? Because these wires, they are going to cut the magnetic field. Now, we know something. We know that when we calculate the line integrals or the surface area integrals, sometimes we have some cosines and sines that show up. So what I will say is that instead of having this drawing, when we do the mathematical calculations, effectively, this is going to be something like this. Okay, like the circuit in red. And now, in this circuit in red, it is much easier for us to figure out in which of these sides the line integrals would be zero. So we don't have to worry too much about the circular path. Now, we can cover an example regarding this. And just for a moment, so what I want to say is the following, actually. So imagine for a moment that we have a magnetic field that is going into the board, okay? And with this magnetic field that goes into the board, imagine for a moment that we have a wire that is like this, okay? And then we can have also another wire that is like this in red, okay? And both of these are moving with a velocity v in this direction, and this one in red is also moving, so they are both moving with the same velocity to our right, as a viewer to our right. And then what we care is that the force which is going to be applied on the electrons here is going to be the Q B cross B. Okay? So if this is the force, then the electromotive force, it will be U, so this is the force, and then we know that the work done, it's force times dl. It is so this is how the work done on the charges will configure. And just for a moment, let me think. Let's try to analyze. I didn't think much about this problem before, but let's think for a moment. we have the same velocity on both of these electrons that are in these pieces, and the V cross B is the same whether it's in the red or in the black circuit, and then we do the integral of dl. Now the force, what is the direction of the force? It looks like the force will also be the same. That's how it looks to me, because V cross B is going to be a force pointing. What is the force here? Because it's going to point upwards. Okay. So this will be the force. It will be pointing upward, and okay. So if the force is going to be pointing upward, this means that for a charge that is here, the force will be here, but for a charge that is here, the force will be pointing up, and here the charge will be pointing up. Okay? So it looks like this is the only difference between these, between the straight line and then this other line. And now another thing that we can construct here is that we can calculate the magnetic field. We can calculate the field for any case where so if we rotate this one across a specific circuit, so if this one rotates, we can find a magnetic flux, a d flux, then we find the rate of change of this flux with respect to time, and this will produce for us an EMF. Let me use this part of the board. So let's assume that we have a magnetic field, B is equal to AY, B0, sine omega t. Okay, so this is the so if we have this circuit that at some instant is here, but probably a little later it will shift, it will rotate to the front, which means that it's going to be here. So this angle, so this is going to rotate in this angle. So here we can assume that we have an angle, let me denote this one as angle theta. And let's see what is the direction of the magnetic field. Apparently we denoted this one along the AY. So this is the B. And it looks like if this is the B, this length, as this is going to be rotated, it will cut these magnetic field lines, okay? And it's going to be this one, okay, and this one at the bottom, which is equivalent actually to this line and this line. So it looks like because of this effective cut of this wire, cutting the magnetic field lines, we'll have a flux and so on. And regarding this, we can denote, let me see for a moment, how we can formulate this one. I guess we can erase this part. And we can keep our final figure. And this force, this will be equal to the force on the charges is always equal to QE plus Q V cross B. Okay, so if this is the force on the circuit, we can, this looks like we have an electric field, effective electric field, which is E plus QV, sorry, this is plus VB, V cross B. And with these two, finally, we can say that the line integral of this effective field, effective electric field, E prime, which is equal to these terms here, this can be written as the rate of change of flux with respect to time times ds minus the line integral of u cross b dot dl. Okay. So the complete EMF, because we see that the unit of this electric field is volt per meter times meter, so this is volt. So this is the effective EMF, and we have two different contributions. One is the change, which is because of the variation of the magnetic field in time, and the other one is because of the motion of the circuit. So since this circuit is moving, we have a non-zero term, which comes non-zero contribution coming from here. And since the magnetic field is also as a function of time, so that's where we have the magnetic field, we have also a contribution from here. We have two contributions that we can make use of them. So, which means that in a transformer, we can have a time-changing magnetic field, and at the same time, we can rotate the circuits, okay? So we can keep rotating the circuits, and we get much more power. So with this expression, I guess we can identify, so if we denote some, let's say that the width of this circuit, this is W, and the length here, let's denote this one, this is length H, okay? And it looks like the surface area of this circuit is equal to W times H. Okay, so area, this is the width times the height. Then with this area, we just multiply with the rate of change of the magnetic field, and we get this contribution. And the other part, so if we consider the general case where the theta is non-zero, because if this one it's a zero, that means that the surface area element and the magnetic field, they make an angle of zero, and then this cosine, because this integral, this means that we have the rate of change of B, dB over dt, times the area times cosine 0 if theta is equal to 0, because we know that the surface area is defined by a vector which is normal to the, so if this is a y, this is also theta, okay? So for a moment, we'll just assume that we have rotated this a little bit, and then the EMF, this will be written as minus d over dt times the magnetic flux, and this whole thing is equal to minus b0 L H cosine theta, and here we take the time derivative of the sine, or let me write it like this, d over dt times sine omega t, because that's what the b is equal to, and this whole thing, this makes this equal to minus b0 omega L H cosine theta cosine omega t. Okay, so one EMF is coming directly from here. Then the other EMF, it should come from the U cross B dot dl. So in this line, U cross B, let's see what is the direction of U cross B. The U velocity, it is equal to so let's see first of all what is the velocity of this part here. The velocity, it should be equal to, but let's also assume that what is the rotational velocity of this circuit. We know that velocity is always equal to R times omega. So if the circuit is rotating like this, fixed at this point, this should be something like this R is the radius. This is going to be equal to W over 2. Let's denote this one because these are both omegas. Let this be the width times the omega, and now the omega is going to be the angular velocity. So this has units of radian per second. Okay. So with these units radian per second, we got this velocity, and it's going to point. Let's see for a moment, this velocity, it will always be tangent to this, to the circular path that this one is going to create. Okay, that's where the V is always going to be. And this one, this is denoted as this EMF is equal to the closed line integral of V cross B dot dl, okay? And again, for a moment, we assume that it looks like this V cross B, it's going to be dl, it's always dx, so the direction of dl is ax, because this is the x-axis, and the V cross B, it's going to be an dot ay. So let's think for a couple of minutes this problem. It looks like from this, okay. So this contribution, we have the velocity and the P, and what we want from there, we want to know also the effective angle between these two components, the surface area element and the AN. And when we do the cross product between these two values, we get AN dot okay, so we know that whenever we take the cross product between the two quantities, the magnitude is going to be equal, so we have this A cross B, it's equal to the magnitude of A times the magnitude of B times sine theta. Okay, that's what we are using here to denote or to figure out how the cross product between these two quantities is going to change. And yes. Okay, so once we enter all of these results here, finally we can write the following. This is going to be equal to the AN times the W over 2 times omega. So now this is the velocity V cross B, where B is equal to B0 sine omega t B0 sine omega t, and this whole thing, this is dot product of AX dx. Okay, so this is what we need to get from here, and then finally if we write for a moment, so we have here when we take the cross product here we should have also the AY, which is the direction of the magnetic field. And from this whole term, we are going to observe that we're going to have a sine theta. Okay, we're going to get the sine theta. And if theta is equal to omega t, and with this omega, we denote also the rotational speed of the circuit. Okay? So this will be sine omega t. So overall, it looks like if the magnetic field is oscillating with the frequency of omega, and the circuit moves with the frequency of omega again, it looks like in the end, we're going to get a sine omega t squared. Okay? And the final result is going to be the following. So we have here omega times the area, so where the area is equal to L times H, or L times, W times the H, this is how we denoted this one, times B0 sine squared omega t. Okay, so this is how the EMF coming from the motion of the circuit. So this will be how much contribution we get from that. And now, if we insert here for theta, also cosine, instead of theta, we are at omega t. So here we can get here omega t, assuming that theta is equal to this. Then it looks like the total EMF, which is coming from both sides of the circuit, we have here, from the both contribution for the EMF, where one of them was changing the P and the other one was the motion of the circuit. If we add up these two terms, it looks like we're going to factor out some term like sine squared plus cosine squared. So it looks like the overall addition is going to be equal to B0 times omega times area. And by the way, this is also called area. What else do we have here? I think this is omega cosine. Wait a second. Yes, but one thing that we have here, we have also a relationship, which is cosine squared x minus sine squared x. This is equal to cosine 2x, right? So we have a relationship like this. So here we have a minus sign change between the first contribution and the second contribution. And here, as a result, we can have here cosine 2 omega t. So this will be the final EMF for such a circuit. Okay. Now, so it looks like this is the way that it looks like the effective electromotive force which is produced in this circuit based on two important parameters. We stated that the B, it oscillates with the frequency of omega, and also the circuit, it rotates with the frequency of omega. The EMF, it is changing with the frequency twice of this omega. Okay, so it moves this is, and let me see in the comment section. Present. Okay, thank you for reporting your presence here in the class. So this is how we can denote how we can find the EMF for any circuit with two important components. Now let's go to some other aspect, but before, actually, the next topic we want to discuss is the wave equation for potential sources. And with potential sources, we have two potentials. We have the vector magnetic potential, A, and the source for that is the current density. And we have also the electrostatic potential V, and the source is the rho. That's what we have. But I'm considering I'm thinking which one is more, which one I should explain first. Okay, so now we are going to talk about the non-homogeneous wave equation for the magnetic potential A and for the electrostatic potential V. What we are going to see here is that remember that we have seen the Laplace equation before, right? So what was the Laplace equation? Just as a short reminder, Laplace equation. We have to apply a Laplace term. This is the Laplace term, okay? Laplace term is defined as the del operator dot del operator, okay? And in Cartesian coordinate system, the Laplace term of any potential, this is going to look like this. The second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. And this operator, this is applied over v, okay? That's the Laplace operator. And we remember that we had this equation before, okay? What is this stating? This is stating that the second order spatial derivative of the potential is equal to 0. And this is the Laplace. But then we had also the non-homogeneous term. Now think for a moment, when do we call something non-homogeneous? I think even in linear algebra, there is a terminology which is equivalent or similar, where we have the following. I don't remember it exactly for now because I'm not very clear, but if this is equal to 0, this is called the homogeneous. But if this is equal to ax is equal to b, this is called non-homogeneous. At the same time, for differential equations, if we have the second derivative of y with respect to x plus 3y, if this is equal to 0, this is called homogeneous. But if this is the second derivative of y with respect to x plus 4y, and this is equal to 3x, the bottom part, this is called non-homogeneous, okay? And the non-homogeneous term, it is equivalent to reporting that we have a source term, okay? So, and when we talk about the source term, we know what that could be. So this equation, which was the Laplace equation, so let's assume that the top part, these are homogeneous equations. So here we have another homogeneous equation, which is equal to 0. But then we can have also the following, where this is equal to rho, okay? So we have three equations on top, which are all homogeneous, and we have three equations on the bottom, which are all not homogeneous. And this equation, which is not homogeneous, this is called the Poisson equation, right? I guess we remember that. So this is Laplace, this is called the Poisson equation. So in the next 5 minutes, that's what we are going to derive, okay? We are going to see how the magnetic potential vector A and the scalar potential of the electrostatic field E, how they change. Now, in order to find V and A, so we are going to erase this part, we need to solve the following. So let's think for a moment. We need to solve this equation. The second spatial derivative of the potential minus the mu permeability times permittivity times the rate of change of the potential as a function of time. This is equal to minus rho over epsilon 0. okay? Now, have you seen this equation before? That's my first question. This equation before, we have seen this, okay? We have seen this because when we did the Poisson equation, it was this. Only that we assume that we have no time variation. Now that we are assuming that we have a time variation, we have to add this other term, okay? And when you look at this other term, I think you might be, if you watch this carefully, you might notice that this term that appears here, this has the units of velocity, okay? So the first thing you might notice is that I have volt. And what is the unit of this whole term? This is volt divided by meter squared, okay? Because you are taking the derivative with respect to space. What about this other term here? This term, this is units of volt divided by second squared. So it's divided by time squared. Then it remains for a homework for you to notice what is the unit of this permeability times permittivity. So you can use your intuition, and most probably it should be easy for you to figure it out, that the unit of this, it should be some velocity. And what this velocity is, you can also predict this one easily, that this could be the speed of light in a medium. Good. So this is the wave equation that we need to solve. And since this is the wave equation that we need to solve, the solution, it should be something like this. The potential is the potential as a function of x and time, okay? We need to find the potential as a function of x and time, and at the same time, this can also be written as an expression of r and time, where r is the distance. And in order to express this one, let's think for a moment that we are going to have let's say here we have x, y, and z, and we have a charge density which is different from 0, which is located here, okay? So here we have the charge density rho, or we can also denote it as delta Q, okay? It's a charge. Then we start solving the equation, but we want to solve this one at a very far distance r, okay? So we have a source here, but we want to measure the effect of this source at a very far away distance. And this distance is much larger than the dimensions of this point charge, okay? So even if so let's say the dimension of this point is like something like L. But now we want to consider when r is much larger than L. Good. Now, we are going to use two approximations. So, well, the first approximation is this one, and the second approximation, or the second thing that we're going to consider is that we're going to assume theta and phi independency. So the problem will be theta, phi independent. Okay, why is this? Imagine for a moment that you have a point charge at the center of the Earth, okay? Why should you think about it? Think for a moment that there is some charge at the center of the Earth, because this charge might be moving or oscillating, and because of this, you get some current, and because of this, you get the magnetic field of the Earth, right? Which is getting weaker and weaker every decade. But forget this, but let's go back to the original argument. At the center of the Earth, you have a point charge which might be oscillating. Then, if you change the angle theta, you are moving from the North Pole to equator, okay? And now, if the distance is the same, you have a theta independence, okay? At the same time, if you are changing the angle phi, you are just switching, let's say, from London to New York, okay? The distance of London to the center of the Earth and the distance of New York to the center of the Earth, it's approximately the same. So we are assuming that if we are using the spherical coordinate systems, the Laplace operator, and you know what the Laplace operator looks like, right? Is this one. So we go to the formula sheet and we see how the Laplace operator in spherical coordinate systems is written. And it's going to look something like this. It's going to have terms like this. Second derivative with respect to r squared plus some second derivative with respect to theta squared plus second derivative with respect to phi squared. But it's not that easy. We have not this easy. We have to also to include the product of each time 1 over h1, h2, and h3, right? And we have to multiply here also with h1, h2. Here we multiply this one with h1, h3. And since this is the first term, we multiply here h2 and h3. Now, what this h1, h2, and h3 are, you do remember those. And these are the necessary parameters to have meters to convert this space derivative, as we're taking the derivative with respect to meters. Fine. But since we're assuming this theta and phi independence, these terms might be simplified. And the differential equation that we will need to solve, it's going to be the following. So allow me to save some space also on the board. This complex equation, Laplace operator in spherical coordinate system, finally, it's going to look like this. So we have this time derivative, the space derivative with respect to r squared delta v over delta r minus mu epsilon, the second derivative of the potential with respect to time, and this is equal to 0. Now, this is equal to 0 because we want to analyze this point P, okay? And at point P, we have no charge density. The only charge density is here, okay? So, since we have no charge density here, this will be the Laplace operator. It's not a point, and if we ask the question, is this a homogeneous or non-homogeneous equation? What can you say about this? Is this differential equation homogeneous or non-homogeneous? This is homogeneous because this is equal to 0. Okay? It does not have a source term to the other side. And now, in order to solve this one, we have to do a change of variables. And the change of variables that we use is going to be the following. We assume that with this v, we write this one as u over r. Okay, so we define a new variable, which is equal to a new variable u. And in this new variable, this equation, this is simplified as the second derivative of u with respect to r squared minus permeability times permittivity times the second derivative of u with respect to time. Now, this is all differential equations. Finally, what it really matters for us is the final solution, which is going to be equal to, so the final solution of this one is that we get a potential V, which is equal to let me write this one. This is equal to 1 over r times any function of time minus okay, so this is the solution of any differential equation. Now, we can do two things. First thing is that we can memorize this expression and we can be happy about it. The second thing that we have to do is to use the intuition and try to understand what this does. So what we see here is that the solution, it's a function of time, but this should be modified by another term, which is r, which is the distance, and this is mu permittivity, so permeability times permittivity. And then we can easily notice that this is seconds, this is meters, so this is second, this r is meter. This means that this term here, it should be seconds per meter, which means that this is 1 over r times a function of t minus r over velocity. Okay, so it looks like the disturbance in space, it propagates with the speed of light. Okay, so in principle, this is the equation. So if this charge is going to move as a function of time, okay, this potential here it will notice the change in this value after some time, which is equal to the distance divided by the speed. So this is equivalent to stating that if we're looking at the sun right now, we see the sun how it was 8 minutes ago. Okay, this is in principle, which means that all of these equations that we solve, these are, so let me write it here, these are called retarded potential or delayed. Okay, retarded potentials. Okay, so we find these expressions, and finally we can write so the same way that we solve these equations for V, we can solve it also for the potential A. So imagine for a moment that instead of V, we write the vector potential A, and we are going to see similar solutions for V and A. And as an answer, we can say that the potential V as a function of R and T, this is equal to 1 over 4 pi times 1 over permittivity times the integral of okay, so this is the potential, the scalar potential, and the magnetic potential, the ART, this is going to be equal to. So these two expressions are so much symmetric that if you remember, whenever we had seen so far, whenever we had the expressions for the V and for the A, the only difference it was that 1 over epsilon, this was equal to mu. So the same thing goes also here. So we just substitute 1 over epsilon with the mu. We keep the same expression here. We are going to integrate over the charge density where it is. And instead of this rho, we're going to write this J minus R over V. Okay? So they're exactly the same, the only difference is that the scalar potential is a function of the charge density, and here the magnetic vector potential is a function of the current density. Okay, so these are called the retarded potentials, and so that's what we have for this. And just notice also a little similarity between this nonlinear equation so if the nonlinear equation, differential equation for the potential, it looks like this, for the magnetic vector potential, it's going to look like this. So the source term, the non-homogeneous source term, here it's a minus rho over permittivity. Here, 1 over the permittivity, it will be substituted with permeability, and rho is J, and that will be all. Okay, so we needed to make notice of this retarded potentials here, because we will need this when we analyze the change in time of the sources. Okay, but from now, let me think for a moment. Yes. So, so once we understand this one, how the source, we can solve similar equations without the source completely, and the meaning of this will be the following: if we just care about how the wave propagates, we can use the sourceless equations. okay? And the time propagation, it will be the same. But if we keep the source, that means that we want to see how the field originates. So there are two things. You either care about how field originates and you look at the source, or you can think more about how the field propagates. Then you can assume as if you don't have the source. But now, so forget about how it originates. Good, it's a source charge, or it's created, but how does it propagate? To understand the propagation, how can we get the exact equation or the correct equation to understand the propagation? For the propagation, we have to look at the Maxwell equations, okay? Because Maxwell's equations, they tell us a lot about how they should progress. So for example, the Maxwell's equation, I think we can make use here. What they look like is that we know what Maxwell's equations are, right? We take two currents and we take two divergences, right? So we take the currents and then we take the divergence, and here we get the divergence, okay? So these are the Maxwell's equations. What do we have on the other side of the equation? Here we have J plus derivative of D with respect to time. Then the curl of E, this is equal to the minus the magnetic field with respect to time. So you can always have the formula sheet, but I personally remember that this is the only place where the minus sign appears. Then this is always equal to 0, and this is equal to rho. Good. So the Maxwell's equation, they tell us how the propagation of E and H move along. Now, what we can do here is that we can, in this curl of H, so let's assume for a moment that we don't have a free charge. Okay? We don't have a free charge. We can have only here, we can take epsilon here, and then, because D, and here we have the rate of change of E with respect to time, because D is equal to permittivity times E. Then, if we have this, the next thing that we can do is that we can consider the curl of E, but the E itself, we can denote the E, let me think for a moment, the rate of change of So what we can apply is that on this differential equation, we can apply the curl one more time. So we can have here the curl of this equation. This is going to be equal to minus mu times the derivative with respect to time. This is a partial derivative, but let me write this like this for a moment. So here we take the mu out, then we're left with the h, but we insert it here. So let's see for a moment. I put an extra curl here, which means that we have to put also an extra curl here. If we put an extra curl here, this is what we get. Okay. Then this curl of h is equal to this part also. So this is equal to minus mu. We have the permittivity, and this will be the second derivative of E with respect to time, dt squared. Okay, so this is what we get here, and finally we can use a couple of approximations here and for vector properties. So let's have a look here, and it looks like combining the first and the second of the Maxwell's equations, or combining the two curls. Finally, the equation that we are going to get will be the following. We are going to get the Laplacian of the electric field minus 1 over the velocity squared times the second derivative of E with respect to time. This is 0. The same thing we can write, or we can derive everything for the magnetic field. So here we can say that the This is intensity 1 over velocity square, the second derivative of h with respect to time, this is 0. So what is this? This is the wave equation. So if someone asked us, define for us what is the wave equation. The wave equation, it's an equation which involves the time derivative and the space derivative. Okay, that's a wave equation. And this wave equation, somewhere, it should have the velocity term. Okay, so now, if you look carefully, it looks like we can derive the wave equation from the Maxwell's ones. So we use these four to get that relationship. Now, that's good. So we are moving a little bit, I mean, so far, we just covered a couple of differential equations, but let's try to make use of them. And in order to make use of them, what I can say is that the use of differential equations, it's a little tricky and it's sometimes difficult. In order to make things much more easier, we use some mathematical construct. And this useful mathematical construct that we're going to introduce is the phasors, or in Albanian we call them Phasors. What the phasors really do is that they are quantities that have no time dependence. Okay, so, and the idea here is that the time, it flows the same for all, so time, it flows equivalently for all quantities, okay? But the other quantities, if we extract the time, they don't change the same way as a function of space, okay? And one representation of this is this, that if two fields or two quantities, they are shifted in time by a constant phase factor. Let me try to take away much of this. So I think the last time we had class together, we derived or we wrote down the two graphs where we had the magnetic field, where the magnetic field, it was some quantity that was changing like this, okay? And from the magnetic field, we wrote down what was the flux. I don't remember exactly what the graphs looked like, but let's assume that, that they're changing like this. Okay? If we see these two quantities, we notice that one of them is leading the other. In this case, the blue line is leading the red line. Okay? So they are shifted. Now, the way that behave here, they're going to behave the same way after a full period. Okay? And in order to simplify the tasks, what we can do is that we can use a phasor. So we can say that this magnetic field, B, is equal to Bs, which is the phasor, times e to the power I omega t. Okay? And then we can have an EMF, which is equal to the phasor of the EMF times e to the power I omega t. Now, the time will progress the same for these two quantities. So what we can do is that we can completely remove this and just look at the phasors. Okay? So it is a mathematical construct, but it is very useful. And when we say mathematical construct, we mean that it's not completely reasonable, or it's not experimentally measurable. So let's see how the phasor notation, how we can make use of it. And what we can do with these quantities, so by the way, this is not electric field, this is the electromotive force. So I'm just linking this one with the case when magnetic field is changing as a function of time, and then we have an electromotive force which is created. Now similarly, we know that electric field also, it originates because of the change in the magnetic field. But for the moment, this is what we mean. Now, let's discuss something about the phasors, okay? Phasors, which the first thing that we should always know is the following. E to the power I omega t minus phi, okay? So what is this quantity equal to? This is equal to e to the power I omega t times e to the power minus I phi, okay? So we get this. At the same time, this is also equal to cosine of omega t minus phi, okay? So these are some relationships which we can make use of these. And let's assume for a moment that we have a current I, which is a function of time, okay? It's going to change as a function of time. And we write this one as an amplitude A0 times cosine of omega t plus phi, okay? Now, let's try to read this one. This is the amplitude, okay? Cosine, it's a function which changes from +1 to -1. Omega is a quantity which is telling to us how often this is going to oscillate, or it tells us about the frequency, which tells us in 1 second, how many times does this one cycle, okay? So this is what omega is going to tell. And this phi, this is the phase constant, or this is the phase of such phasa, because this is the whole thing, this is phase, okay? Because this is measured in radians, and we find the cosine of some quantity in radians. And at time t equal to 0, we have an inherent, so even at time t equal to 0, if phi is different from 0, we call that one initial phase difference. Good. And what we want to do now with the phasor notation, we want to take this out, okay? We don't want that one which is circled in red. We don't want the time, because, as we said, time, it flows equivalently for every quantity. So, in order to solve this problem, we assume for a moment that we have the, let me think, let's see for an RLC circuit. In an RLC circuit, which involves one resistance, one inductor, and one capacitor, so for any RLC circuit, we have this equation. We have L times di over dt plus the resistance times the current plus 1 over the capacitor times the charge, which is equal to I dt, because all of these quantities, these are measured in volts, okay? That's the potential difference across a circuit, and this is all equal to the alternating the AC power supplier, the V as a function of time. And now we have here that this IT, this current as a function of time, we want to write this one as the, let me think for a moment, this is equal to, we want to write this one as the real part of the phasor, which is Is, e to the power I omega t, okay? So that's what we're going to write for the time. And then, so here we have the real part of Is e to the power I omega t. You're not very lucky with the pen today. Then the di over dt this will be equal to, so if we see what is the rate of change of this one with respect to time, we're just going to get an I omega, okay? Because that's what the derivative produces for us. This will be equal to the real part of I omega times Is times e to the power I omega t. Okay, that's the, and then the integral of I dt, okay, because we have three different quantities. We have the rate of change, we have I, and we have also this integral. Okay, so we can write them one separately. So this I dt, this is equal to the real part of the phasor divided by I omega e to the power I omega t. Okay? So if the current is changed as a function of time, like this expression, the time derivative and the time integral is going to be like this. So we substitute all of these three terms in this RLC circuit equation. If we substitute them, if you substitute them, finally, we're going to get the following. We're going to get the real part of Li omega times the phasor. So we just multiply by L, this derivative, e to the power I omega t, plus R, the real part of phasor, e to the power I omega t, plus 1 over c. Then we have the real part of Is over omega I e to the power I omega t. This is equal to Vt. So if this is the case, we can simply, let's write this one Vt also as the real part of the phasor of the potential e to the power I omega t. In few textbooks or many textbooks, instead of I, you can notice also J. Okay, they are both square root of -1. And here we see that the time factor, if we use the phasor notation, it can be cancelled everywhere. So we just cancel it. And as a result, we finally get the following. We get that J omega LIS plus RIS. Now, IS, this is the phasor, okay? Phasor IS. And plus IS over J omega S. This is equal to VS, okay? So this is what we get. And the thing is that what we want to find, the question at this point is this. What is the current phasor? Okay, that's what we are getting for the moment. So we have this expression here. Let's just try to identify what is the current phasor. All we need to do is that we just need to factor out these terms, the Is, right? It's easy. It's all linear. We don't have any nonlinear term that we may need to take the square root or any complex expression. We just say that the Is, this is equal to the phasor of the potential divided by what? Here we have R plus J, and here we have omega L minus omega L minus 1 over omega C, okay? So we got this answer. So this is the phasor for the, so this is the phasor of the potential, and this is the phasor of the current in the RLC circuit. So this is just a reminder of how we make use of the phasors. Now, I'll just go over one final example. So I hope that this part is clear. Now, So before a while, before a couple of minutes, we had the Maxwell's equations on the board. And the Maxwell's equation, let's not forget, we had two curls and two divergences, and they were equal, the curls there. So in order to remember the Maxwell's equations, you can also remember this sentence. The curls of the intensities, they are equal to the, and curl is the derivative of 1 over meter, right? These are equal to the rate of change of the fluxes, okay? Which means the following. What is the curl of E? The curl of E is always equal to the d over dt, the time change, of the flux of the other field, or of the respective field. So if this is electric, this should be magnetic, okay? Then the curl of H, so if you put here H, this should be, instead of V, you put D. Okay, so this is how we relate, how we can write the, so, and now, the reason I mentioned this one is that since we have this time derivative, d over dt, if we use the phasor notation, when we put d over dt, we get some I omega, okay? So this means that when we write the Maxwell's equations in phasor notations, we have the following. We have the curl of E. This is equal to minus R j omega mu h. Good. So that's the first curl. The second curl, which is the curl of the magnetic field intensity, for sure we have j omega. Okay. But this is the time change. So this j omega, this represents the time derivative. Okay. So j omega in phasor notation is this, because d over dt, this is equivalent to j omega. So you can write this somewhere. And this is j omega, and this is permittivity times E. And these two are flux, and these two are flux. Okay, so with this new representation of the Maxwell's equations, let's try to make use of these right away. So let's see this example. Let's assume that we have an electric field which is as a function of z and t. If an electric field is a function of z and t, that means that this is propagating along the z-axis, and of course, as time passes, it's going to change. But this does not mean that the electric field, the vector, is along the z. But this can be, this is equal to ay, okay, times 5 cosine 10 to the power 9 t minus beta z. Okay, so here we have the equation of some electric field. Now, let's try to understand what this is. This is on the top. Let's write this. So phi is the amplitude. Cosine, which has a limit from plus minus 1, this is always going to be equal to omega t minus beta z. Okay? So at this moment, what is omega? Omega, so these are the Maxwell's equations, let's keep them here. But we are given this expression, 10 to the power 9, so it looks like this is gigahertz order of frequency. And this omega, we can write this one, this omega is equal to 2 pi f, and this is equal to 10 to the power 9, which means that the frequency that we're talking about is something like 1 over 2 pi times 10 to the power 9. 1 over 2 pi is 1 over 6, which means that this is something like 10 divided by 2 pi times 10 to the power 8. 10 to the power 8, it's something like 100 megahertz, okay? So this is in the order of 100 megahertz or 0.1 gigahertz. But this is how we try to read this expression. Now, the question is, is the following. Find H and find beta. Okay, so it looks like we have a single expression and we have to find two outcomes. One is a magnetic field, the other one is the B. So if we have the E, can we find the H? Yes, we can. Okay, so here we have the curl, because we have E, we can apply the curl and we immediately get the H. It's very easy. And we do this using the Maxwell's equation. But to do this, it's always good to use phasors. Okay? We use phasor, which means that let's remove the time dependency. When we remove the time dependency, we remove it this way. We say that E as a function of Z and T, okay? But this T, we cancel it out. This can be written as the amplitude times e to the power minus I beta Z. This is the phasor, okay? And again, let's look for a moment, what is this cosine? Cosine is equal to the real part of e to the power 10 to the power 9 time minus beta Z, right? This cosine is this, right? So if this is the case, we can even write this one, that this is equal to the real part of e to the power 10 to the power 9 t times e minus, we have forgotten to put the I or the J. So here we have another I minus I beta Z. Okay? So cosine is the real part of this. We get this. If we cancel out the time, that's what we are left with. So the phasor is this, AY. Now, why is this AY? Let's assume for a moment that this is x-axis. How can I do this better? No, this is z-x. Let's have the x-axis like this. Or x, y, z, x, y, z. X, Y, Z, okay. So this X, Y, Z, this means that we have a wave that is going upward, but the electric field is going to move like this. So electric field is pointing like this, but the wave or the photons are moving upwards. So that's what we denote, but now let's try to solve the problem. To solve this problem, it takes 2 minutes, okay? That's all. And for these 2 minutes, we just write the following. Let's see it for a moment. From the first expression, we find that H is equal to minus 1 over I omega mu. That's it, okay? Times the curl of E. So we get this one from this equation. And what is the curl of E? Is this AX, AY, AZ. Derivative with respect to x, derivative with respect to y, and derivative with respect to z. And here, what is the AX? This is 0. What is the component of E along the y-axis? Is 5 e to the power minus I beta z, and this is 0. Okay? So this whole term here, this is curl of E. Okay? So this is how we get this from the Maxwell's equation. Then we follow all the steps. So we just calculate what the curl is here, and the final answer is the following. This is equal to minus AX. Okay, that's the direction that we get here. Beta divided by omega mu 5 e to the power minus I beta z, okay? So apparently, we found what the H is, okay? Now, so we solved the first part. And then, we also noticed that the H and the E, they are perpendicular to each other. So one is pointing along the AY, the other one is pointing minus AX. Okay? But now we have another question, which is find the beta. So it looks like this beta is a quantity which is strongly related with the other parameters. And that's why we should be able to find it. So in order to find this one, what we can do is that we can use the other Maxwell equation, okay? Which means that using the other Maxwell equation which is on the board, this H that we know now, so this one, let's apply the curl one more time, okay? And the electric field, if we look at the second equation, we can write that E is equal to what? Let me see this. E is equal to 1 over J omega permittivity, J omega times permittivity. Okay? J omega permittivity. And then we have to put here AX, AY, AZ, derivative with respect to X, derivative with respect to Y, and derivative with respect to Z. And then we look at the components of H. H is all in here. This is minus beta over omega mu times 5 times e to the power minus I beta z. Okay? Then it has 0 component along the y, and the component along the z is also 0. Okay? So we just try to solve this one, and for the E, what we find about the E is the following. So finally, this will be equal to AY times beta squared over omega squared permeability times permittivity. Okay, because if you look at it carefully, you're going to see that this term is going to multiply this term. So we get all this set of terms here times 5 e to the power minus I beta z. Okay. Now, for a moment, this is the answer. So we have this. So let's see for a moment. We have this E. Okay. Using the first Maxwell's equation, we have this E. Using this, we found this H. Using this H, we found this E again. Now, it looks like this term should be equal to this term, right? Of course, because they are both electric fields. And then let's cancel the terms out, and it looks like this 5, it can cancel this 5 in here, and this exponential term is cancelled this. So what we are left with this beta squared over omega squared times permittivity. This is equal to 1. So let me find some useful space. And it looks like beta squared over this square, this is equal to 1, okay? And we need to find the beta. So beta, actually this part, this was the first curl. So it looks like beta squared is equal to omega squared times this, and this is equal to, what is omega squared? Omega squared is 10 to the power 9 squared. Okay? This is 10 to the power 9 squared, and the permeability times permittivity, this is equal to 1 over c squared. So this is 1 over the speed of light squared, which is 3 times 10 to the power 8 square here. Okay? Then we check here, and beta squared is again equal to 10 to the power 9 squared over 10 to the power 8 squared. So, but let's first of all, let's write this one. 1 over 3 squared times 10 over 10 to the power 9 over 10 to the power 8, we get 1/10. We get another 10. So this is equal to 100 divided by 3. So apparently, beta is equal to 10 over square root of 3. Okay? We found it. So this is a small exercise of how we could make use of the phasors. If we had cosines and sines, we know that we can do it also that way. The mathematics, it will be the same. But using the phasors, things are simpler. Do we have any question? Okay, thank you for your attention. We can still get questions from you.